Hi everyone, my name is Wenyang, and today I'm going to talk about my recent work on MWA Phase 2 EOR power spectrum at Redshift 7. So I'm working with MWA Phase 2 compact array, improved power spectrum sensitivity, and good imaging capability. The array is unique that we can apply both sky-based calibration and redundant calibration. So the data I'm looking at comes from the EOR 0 high band, corresponding to Redshift 7.5 to 6.2. The observations were taken in 2016 from October to December. There are 13 days of data, 40 hours in total, 1,255 observation snapshots. The analysis pipeline I'm using is FHD Epsilon, which is the US pipeline. We use FHD for program modeling, calibration, program subtraction, and imaging. And the images, the per observation image output of FHD are headed to Epsilon to produce power spectrum. So I also use take the RTS chip, which is an independent analysis pipeline, take the results as a validation, compare that with FHD Epsilon. So I've done some modifications to the FHD Epsilon pipeline. So first I've added a quality control step. I implement 3 quality metrics to better evaluate the data quality. I've also integrated redundant calibration to the calibration step, and I've also improved the bandpass calibration, which I will talk in a little bit. So first, quality metric. The first quality metric is already introduced by Mike, using the sky subtracted incoherent noise spectrum. So we difference the visibilities in adjacent time pairs. Take the amplitude. So this delta V should follow a relay distribution. So in a relatively clean observation, you can see the incoherent noise spectrum calculated from the data matches pretty well with this relay distribution. For a contaminated data by R5, we can kind of see a very long tail. So if we average this delta V across all baselines, we get the top panel. You can kind of see some faint structures in the middle. This is from channel 7. So here I did a little different thing from Mike. I divide the median value of each frequency channel because I'm afraid that some outliers might make the mean being very large. So, but either way works. So if I flag these time frequency samples based on, say, 5 standard deviation thresholds, it's not good enough. So I kind of developed some further filters. I convolve this waterfall with Gaussian kernel in frequency with 4 with half max of 0.64 MHz, and again use 5 sigma to flag the sample. That's better, but still I'm not quite comfortable with that, so I did more aggressive flagging. So I just flag the whole time slice. I also do some frequency coherence flagging check. I don't have time to talk about that. So the next quality metric is Chi-12 redundant calibration. So in phase 2, we can calibrate these redundant baselines from the hexagonal subarrays. The Chi-12 is calculated in this equation. So the V is the measured visibility. The gains and the true visibilities are solutions from redundant calibration. So this sigma corresponds to the noise level. So we can sum up this across or redundant baselines. There are over 2,000 baselines in this sum. So the degree of freedom is number of baselines minus number of unique baselines. So this chi-square should be centered 1. So when I calculate chi-square, I can see some of these features in the data. So this is again channel 7, and this RFI is very thin and highly polarized. I only see that in the east-west polarization. So if I just take out of the channel 7 data, I get very nice distribution. So the thing I want to highlight here is that this RFI cannot be captured by things. So this RFI first is very time stable. When you calculate things, this RFI also gets subtracted. And a possible scenario of this RFI is some bright RFI which is very close to the horizon. So part of the array is, has very strong response to that. So this is chi-12, and the third quality metric is the window power. This is kind of, I would say, an ultimate metric. So I calculate the power spectrum for each individual observation, and plot that as a function of local sidereal time. Also, MWA has the MWA shifts the pointing every 30 minutes. So there are 10 pointings here. In this data set, we don't have the 3 and 4 pointing 3 and 4. So for -5 and -4, our calibration just don't converge. So the bright Milky Way get into the side lobe becomes dominant, and we can calibrate that. So the remaining of the pointing, I make per observation power spectrum. Yes. Okay. So I make per observation power spectrum showing only right plot. So we can see the -3 pointing is highly RST dependent. That means our calibration is still not good enough. The unmodeled sources is still affecting our calibration, so we basically take it out. So for the remaining observations, Y is pretty, north-south polarization is pretty clean, but the east-west has a lot of contamination, especially +1, +2 pointing, so we take out these observations. So next I'm going to talk about my improvements in the calibration. First, I do redundant calibration. Combine that with guide calibration. I call it hybrid calibration, and compare that with guide calibration only. We can see first they have good agreement, but they have level a few percent difference. In both cases, the coarse band edges show the most difference. So to compare the calibration, we compare that in part second space. So I'm going to show 2D part second here. So the last one is the guide calibration only. The middle has the hybrid calibration. They look identical, so we make a difference. Shows on the right. Blue means hybrid is better. Red means makes things worse. So definitely the hybrid calibration is better in the coarse band mode. So if we look at the modes other than those, we must put the coarse band mode here. So these shaded region are noise level. This is the indigo line is the EOR level. So I show the absolute difference between these two the power spectrum from using these two calibrations in green and red line. So this solid line means the hybrid calibration is helping, and the solid line is not helping. So first we can see the cable reflection mode at 150 meters and 230 meters, maybe just Y. There are some improvements, but they are kind of marginal because they are below the noise level. So we keep asking if we can do it better. So Barry 2016 has argued that to mitigate the contamination in the EOR window, we should constrain a smooth bandpass. So in BOC 2016, we use the per cable type bandpass. The cable is the cable connecting from the beamformer to the receiver. So and feed a second order polynomial in the amplitude linear to the phase, and and a sinusoidal term for the cable refraction. So in this, in my work, I use the autocorrelations to capture the antenna-to-antenna variation, which is defined here. I want to remove the global sky signal from the autocorrelation. So I did this. I took a reference antenna and divided out from the auto of each tile. So this is the final bandpass calibration. So if I do this per cable type bandpass, so showing on the top, we do see like different cable types show different bandpass. So if we plot the bandpass for all tiles in gray and calculate the global bandpass average across the whole tile in black, so we can show a lot of variation, and we've washed out a lot of frequency structures. But if we remove the scale autocorrelations from each bandpass of each tile, then do this per cable type bandpass, we can see they agree pretty well. So this gave us the motivation to do the global bandpass average, and this gives us more samples to average, washes out more frequency structures, artificial frequency structures introduced by incomplete sky model, and the smooth autocorrelation also makes the calibration more smooth. So cable refraction also helps capturing the cable refraction. We can see very strong clean ripples from the autocorrelation. So we can use that to hyper-resolve the reflection modes and use those modes to fix the calibration. So finally, we compare the calibration in cross-spectrum space again. So one with the old calibration, the other with one with the old bandpass calibration, one with the new bandpass calibration, and we make a difference again. So solid again means the new calibration is better. So we can see that now this makes a significant improvement. So the cable refraction modes, they are well above the noise level, and the modes below the first coarse band are all improvements, and they are up to 10 to the 4, which is definitely comparable to our current power spectrum limit. So finally, I'm going to talk about the power spectrum results. So this is the just showing the case-based selection in the power spectrum. I have time, so I'm going to skip that. So this is the analysis validation comparing the FHT epsilon with RTS chips. So we can see in general they have fair agreement, and the noise level. So FHT is slightly higher. This can be explained by my flagging using things, because I'm using that 2 flag model. So this is the so then I do the 3 Redshift power spectrum. So each subband takes about 15 macros because I'm applying a Blackman-Harris linear function in frequency axis. So the effective dynamic range in frequency is 7.5 megahertz. So this is the final 1D power spectrum. You can see that the modes between the first and second coarse bands are mostly noise dominated. And comparing that with usually at our 2016 results, which is shown in cyan, so I have significant improvements. And we can also see some radic signature of the 150 meter cable refraction in 2016 results. But in this work, we have removed this cable refraction effectively. So it's starting to put the new results into this plot, although this is still preliminary. So I'm running out of time, so I'll take questions.
I thought you were showing with the bandpass calibration improvements.
Yes.
Is that comparing your old method with the auto-based one, or just comparing with and without redundant?
So the base calibration are the same, just sky calibration. So one with the old bandpass calibration, one with the new bandpass calibration.
Okay, thank you.
Maybe a completely stupid question, but why are we building dual polarized telescopes to do the EOR?
Good question.
It helps with our foreground understanding.
Which is could halve the cost of the telescope.
We also would have guessed the wrong polarization.
You're saying when the astronomers have got the choice of one polarization, they'll still get it wrong.
Or this astronomer would have gotten it wrong. I would have expected the other one to be better. Early results, that was, not in the last 3 years, but the early results, we got a little better, if memory serves, on the east-west, and now north-south is the system.
It's a significant worry that there's any difference.
I think that Nicole was saying probably our next call central is putting in a model for the piece to help us calibrate, to help us recover the large scale mode, and that's 50% polarized. And so that's when we're really going to use that polarization.
Matt's going to talk about that too.
I